Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
So we'll kick off then with limits. We're going to recap workshop number 7 first, just to pick up where we left off. Now, if you remember, we posed this question in workshop number 7. Is €2 the best possible return if I invest €1 after 1 year with an interest rate of 100%? Okay, so last workshop we did a lot on compound interest. Okay, so here we have our compound interest formula. That's the principal times 1 plus I to the power of n. Okay, where I is our interest and n is our compounding periods. So in this situation here we have my principal is €1, my interest is 100%, so we write that in decimal form, so that'll just be a 1, and our compounding periods is just 1 year. So if we put all of this in then, what will we get back after 1 year with 100% interest? We'll actually get €2. So the question here is, can we do any better than €2? Okay, now how you can actually do better than €2 is by asking the bank or the credit union to compound your interest differently. So you're still getting interest over a year, but what you might say is, listen, will you give me interest twice during the year instead? So will you break up my 100% and give me 50% after 6 months and give me 50%, the other 50% then after the other 6 months? And when you do that, putting this into your formula, we have €1, and this time our 50% then will be represented as 0.5, and this time we'll have 2 compounding periods, okay, 6 months and 6 months. And when we do this out, we see that we get €2.25. So isn't that brilliant? If you get your compound interest done differently, you will actually earn more money. Now, for the sake of ease, actually, what we tend to do here is we relate the interest to the power, the 2 compounding periods. So it's easier to write it as my 1 for my 100% divided by 2. So you'd say 1 plus a half all to the power of 2. So setting up that model, what we said to the kids was, oh my God, I wonder will this keep working? What if we go in and say, will you give me my interest every 3 months? Am I going to earn more money? Maybe somebody will get smart and say, well, if you give me my interest every month, I'm going to earn even more money. So we kind of got their curiosity going, and we give them an activity sheet to do. So do you remember doing this? Where they had to investigate then every month, every week, every day, every hour for compounding their interest, every minute, every second. Okay. And sure enough, at the beginning, we see that we are earning more and more money. This looks like it's brilliant. Okay, all the kids are running into the credit union now. They think they've nailed this. Okay, but what do they find as they go through this activity and they get down to every minute, every second?
It approaches a limit.
Yeah, it approaches a limit, absolutely. So it gets to a point where they're just earning 2.718 and it's not improving. Okay, certainly not past their 2 cent worth. Okay, so 2 decimal places of cent. So it has hit a limit. Now, what we did was, that was kind of the first time, say, a class was introduced to this idea that a number can hit a wall. So in workshop 7, we thought this was a lovely activity to introduce the idea of the limit. Okay? So looking at this, we looked at the limit, and then we also then put our proper notation on it. So instead of telling this function, okay, so what's our function look like now? It's because it's 1, it's just really 1 plus 1 over n, all to the power of n, isn't it? That's what they have been looking at, say, in terms of a function. And instead of telling that function, okay, let the compounding periods get really big, because if you're doing every second, isn't that a massive amount of compounding periods? So the more mathematical way of saying that, instead of saying let the compounding periods get really big, is we say take the limit of this and let the compounding periods approach infinity. So you're saying let them get bigger and bigger and bigger and bigger and bigger. And what happens is, no matter how big they get, they still hit this wall of the limit. Isn't that it? So our limit then was this number here, 2.718, and so on. Now, I say and so on, okay, because what's happening way down here?
It's still changing.
Yeah, it's still changing. It's just that the change has gotten so tiny that it now is negligible. You can ignore it. It's so tiny that you can ignore it, exactly. So a limit is really a lovely idea for practical purposes, okay? You're saying, okay, I'm using that number practically because my changes have gotten so infinitesimally small that we can just ignore them, okay? Now, this number here then, it's actually an irrational number, and it's the constant e. So that's what that number is. It's the constant e. And so this, if you take it that one wee step further, you're bringing it up to honours leaving cert level, aren't you, to introduce this idea of e. Right, so that equals e. Now, if we look at a little demonstration of that, just going to use a little Geogebra file to look at a diagram of what we're after doing here. So here is my €1, okay? And here are my 12 months, okay? So €1, it stays the same. You see the flat line? It stays the same for the whole year, but at the end of the year we put on 100% interest and it jumped up to €2, okay? But what we were doing was, that was just with one compounding period. When we broke that up into 2 compounding periods, this is what happened. So for 6 months, it stayed, my €1 stayed the exact same, but after 6 months, I added on 50% interest. So there's my interest, okay? Now I have this amount in the bank, and it stays at that level until I add on the second 50%, okay? So, and this time now I've gone up to €2.25, okay? So this is a lovely demonstration because you can kind of see what happens as you have more compounding periods, okay? But what's lovely here is, this model here is the compounding periods getting massive, okay? So we're going to have a look at what happens on a diagram as my compounding periods get really big. Yeah. Can you see what's happening? They're nearly joined together, aren't they? So what you find is when you let your compounding periods get really big, that it becomes a model of continuous growth. Can you see that? Now, you know and I know it's really made up of steps. But the steps now have become so tiny that we've gone from discrete to virtual continuous. Okay? So what we say is actually E, another way of talking about it, is the base of continuous growth. Okay? So it's a base for continuous growth. Okay. So that's why the kids, the leaving certs, they have to deal with e to the power of 2, e to the power of 2x. They have to be able to differentiate it, integrate it. It's because e as a base with a power is very important because of its ability to model continuous growth. Okay, now why this is really nice is we can kind of look at the limit here from two angles. We looked at it from the point of view of the compounding periods getting massive. Okay, what if we looked at it from the point of view of the intervals? These little intervals. What's happening to them as my compounding periods get bigger? Yeah, they're getting smaller. Absolutely. So I wonder, we could nearly say that this was the same as my little interval tending to 0. It's kind of the same difference, isn't it? Your interval tending to 0. And I think that's kind of a nice thing to look at, because you and I know where we're going with calculus. And in calculus, it'll be the interval that's tending to 0, isn't it? So it's just another way of looking at it. So that's where we finished off in workshop 7. And what we're going to do then is we're going to bounce forward then and take the limit a little bit further. Okay. So as we said there, a limit, it's brilliant for practical purposes, okay? And what we want to do is have a wee look at these two examples. See this one here. Can we say that y is nearly or practically equals 4 when x equals 2 in the following? So when x equals 2, you can see here, I've got nothing. I've got no value. Sure, I haven't. But if I wanted a practical value, if I needed a value for there, okay, what could I practically say it was? What would it nearly be? 4. And would you be happy with that in this case? Yeah, okay. What about this one? Again, we have a situation here where we've got a 2. We've got the value of 5, but then we've got another situation here where we have no value at the end of where it approaches from the left-hand side. So can you see over here, we said this was practically 4. But if we were coming from the left, it would look like that was practically 4. But what if we were coming from the right? It's actually 5. So you kind of have this jar from the left and the right, don't you? Okay? So it would be okay to talk about it here, whereas you can see here, there's a jarring situation from the left and the right. Okay. So when we're talking about limits, the practical value we use is called a limit and exists if the function approaches the same value from the left and the right. You have to have that consistency from the left and the right. Okay, so we're going to do a little activity now, but before we do, I just want to ask you these 3 questions. So assuming that the domains of the following functions are over or, the real numbers, write out the accurate domain for each function. So for the first one, f of x equals x plus 3, we would just say x is an element of or. Isn't that right? So the domain is over the real function, so it's x is an element of or. Now, how would we write the domain for the second one? X squared minus 9 over x minus 3. Yeah, absolutely not equal to 3. So we've x an element of or, but x cannot be equal to 3. And what about the last one? Yeah, absolutely. So it's the same again. So with these functions here, we can see we don't have an issue with the first one, but with the second two, we have a little hole in our function, don't we, where we can't have it equal to 3. So that's what we're going to do an investigation around now. Okay, so this is the one we're going to be investigating, is the 3. Okay, and what I want you to do is I want you to see how the function behaves coming from the left hand side. So we're going to evaluate this function at 2.9, 2.99, 2.999, etc., coming up to 3. So what we say here is these values are approaching 3, aren't they? So the value's approaching 3, we're going to see what the y value is. And then when we come from the right-hand side, these values are approaching 3 from the right. And we're going to see what the y value is that they approach. Okay? Now, what we're going to know is that actually when x equals 3, we don't have a value here for this function. Sure, we don't. Because we said x cannot be 3. And for this one, x cannot be 3. So we're not going to have a value here or here. But what we're going to be interested in to see is, does it behave on the left the same as it behaves on the right? Because if it does, we'll be allowed use a limit for a practical value, but if it doesn't behave on the left as it does on the right, we won't be allowed, okay? And then you're going to be able to answer these questions. Okay, so having a wee look there at your workbook. So this is on page 3, and you have calculators there on your desk. So will you just have a wee go at that, please? And where that activity is going. So that's a lovely one for the kids to do in the classroom. It's really just a lot of calculator work as well in the activity, isn't it? And they're getting a feeling for the values approaching either side. So what we have then is, as we look at the first function, f of x, we see our values are clearly approaching 6 from the left, and they are approaching 6 from the right-hand side. And we know that the value is 6, so there's a lovely continuity across the pattern here. Having a look at the g of x, we see that as well, it is clearly approaching 6 from the left. We know we don't have a value here because x can't equal 3, but from the right as well, we seem to be approaching 6. So there's a lovely continuity from the left and right here as well. Okay, so that's good. H of x then, if we look at the values there, we can see that from the left, we seem to be approaching minus 10,000. Okay, so we seem to be getting very big on the left, don't we, with the negative numbers, or very big negative numbers on the left. And then when we come from the right, we seem to be getting towards a very big number, but it's a positive one. So is there continuity from the left and the right on the last one there? No. No. Okay. So the last one is going to be an issue. So having a look at these then, when x approaches 3, does the value of each of the following functions approach a fixed value? And that's if it does from the left and the right. And if so, find the value. So we saw the first one approached a fixed value, and we expected that would be okay, no problem. The next one then, we see that it did approach 6 from the left and the right, so it is approaching a fixed value. And h of x, we saw that it's approaching different values from the left and the right, so we cannot say it approaches any sort of fixed value. Okay. So having a look at the geometrical meaning of a limit of a function then, what we can say here is that as x approaches 3, in this function, the first one, we're approaching 6. The y's are approaching 6. So can you see what's happening here in this diagram? See the way my x's are coming in closer to 3? And what's happening correspondingly is my x's or my y's are coming closer to 6. So as x approaches 3, y approaches 6, the fixed value of 6. So with the limit as x approaches 3 of f of x equals 6. Okay, this one here then, g of x could not equal 3. So as we already realized, there was a hole in our function where we didn't have a value for x equals 3. But what we did see was, as we approach from the left and the right towards the 3, correspondingly up here, my y values are approaching 6. Okay, so that means it is okay for me to say the limit of g of x as x approaches 3 is 6. Okay. Now this one then was different, and we can see why. A picture tells a lot, doesn't it? Okay, so the picture is very clear here, where we see that as we approach 3 from the left and the right, coming from the right, my y values are getting bigger, and as I approach from the left, my y values are getting smaller. They're going down negatively. So as x approaches 3, we can see my y's go opposite directions. So no limit exists. Okay. So what we're going to have a look now at are continuous functions. Okay. So what is a continuous function? For a function to be continuous at a point, it must fulfill all 3 of these conditions. Right. Now, before I look at the conditions, let's just talk about intuition. Right? Continuous, what do you think continuous means? There's no break, there's no hole. Exactly. That's what continuous means to us. So before we look at the conditions, let's just see. Do you reckon the first function is continuous?
Yes.
Yeah. Do you reckon the second one is?
No.
No. Do you reckon the third one is?
Nearly.
Nearly, but not. Exactly. So it's nearly, but there is a hole in it, so it's not. Okay, so that is not continuous. But if we're looking at the maths way, you have your intuition, but the maths way then is it would fill these 3 conditions. So if you're talking about at a certain point, let's say we were wondering, is this continuous at 2, and at 2, just to focus what we're looking at. The function must have a value at the point, okay? The function must have a limit at the point, and the value must equal the limit. And in that case then, the function is continuous at the point that you're looking at. So the point of interest up here is 2, because that's where all of the interest happens up here. So the first one we can see, we do have a value at 2. Also, we have a limit at 2 because it behaves the same on the left as it does on the right. And my limit would be 4, and my value of 2 is 4, and the 2 equal each other. So mathematically, we say it is continuous at 2. This one here, I have a value at 2. My value is 5. But as we saw earlier, we don't have a limit here because it is approaching a different number on the right as it is on the left. So we don't have a limit. So it falls down on number 2. And the second one here, we can see we have a limit, okay, because it approaches the same number on the left and the right, but we actually just don't have a value at 2. So it falls down on the first one. Okay. All right, so we would say if it is not continuous, then it is discontinuous at 2 in this one, and it is discontinuous at 2 in this one. Okay. So is this one here continuous? No. Intuition says no. This one is not continuous. And then if we look at it as well, we do have a value for 3. It's 3. But what do we not have? We don't have a limit. Different on the left as it is on the right. So this is not continuous. Is this continuous? Intuition says no. And again, here's where we see the third one kicking in, because we do have a point at 3. So the value when x equals 3 is 3. And we do actually have a limit as x approaches 3. Exactly, the limit is 6, but the limit and the point are not the same. So it is not continuous. Okay. So again, so is this one continuous?
Yes.
Is this one continuous?
No.
Now, is this one continuous?
Yep.
What does your intuition tell you?
Yes.
Yeah, if you think of it, are there any breaks? No, so yeah, this one is continuous as well, even though it looks a little bit unusual. Okay. So there are, if you look in your booklet, there are more questions that you can do back at school with the kids. There's more questions there for you to work with, okay? So what I'm going to use for this section is the T&L in PowerPoint form. So you know the way you get a T&L in most workshops, and then all of those T&Ls have been put onto projectmaths.ie in PowerPoint form, so that when you're in the classroom you can be clicking through all of the activities in the T&L. Right, so they're there for you to download. So I thought I would use those, the corresponding PowerPoints for this T&L, and you'll be able to follow the T&L as we go. All right. So what we're going to do is we're going to kick off there on the very first page then of your T&L. Yeah. So our very first question then for our class. So we're in a gang of 5th years now coming in from their Junior Cert. So today we are going to look at rates of change. Okay. So where for your Junior Cert, you're going to be my 5th years now, okay? So where for your Junior Cert have you already seen rates of change? In your slope. Absolutely. So you've already seen rates of change in your slope, and they learnt their slope in lots of different ways. So they would have done then slope through patterns, isn't that right? So they would have seen slope in a relationship. Just trying to think of, you know, what's the prior knowledge? What are they coming in with? Rise over run, brilliant. How else have they looked at their rate of change?
Coordinate geometry.
Coordinate geometry, perfect. Absolutely. Anywhere else? Tan, brilliant. Okay, lovely ratio there. Okay, so and we also looked at it. Do you remember when we were trying to get them to look at relationships? We would have used a table, and we would have gotten them to check the change in between the y values as well. So that's investigating their rate of change if they wanted to see if there's a constant rate of change. That would be in the line. So there's a lot of this kind of work in Junior Cert, and that's what we're going to bounce off now for getting into calculus. Right. So what I'd like you to do now is, you see this formula here, y2 minus y1 over x2 minus x1. Here's what we have here. That's exactly what this is, measuring, isn't it? Here my x2 minus x1 is a measure of my run, isn't that right? My y2 minus y1 is a measure of my rise. And these over this gives me my slope. So in words, what exactly are we measuring here? You know, when you get the slope of a line, what are we measuring?
The rate of change of one over the other.
Yeah, the rate of change of one over the other. So it's the rate of change of the y's over the x's. Okay. So which one is sort of changing first? Which one is changing as what one is changing? Yeah, your y is changing as your x is changing. So that's what we're getting a measure of when we get slope, isn't it? How are my y's changing as my x's change? So as my x's get bigger, are my y's getting bigger? Or are they getting smaller? You're investigating the behavior of the y's as your x's are getting bigger. Okay. So if we looked at this one here, we have a slope of a line here, y equals 3x. So this is my line. What is my slope then?
3.
Is 3. So explain to me what the 3 means then.
For every 1 unit change in x, there's 3 in y.
Perfect. For every 1 unit change in x, there's a change of 3 units in the y's. And could we put some signs on them? So your x's, in what direction are they going?
They're increasing.
They're increasing, and won't they always be increasing? Okay, because won't we always be reading our graphs from left to right? So my x's will always be increasing. So as my x's increase by 1 unit, my y increases by 3 units. Perfect. Okay. So what will this one be then when my slope is minus a half?
So every 2 units Or 1 unit decreasing in the y.
Perfect, perfect. So as I increase by 2 units, my y's will decrease by 1. Or as I increase by 1 unit x, my y's will decrease by half a unit. Perfect. Okay. So what we're going to do is we're going to give some context to the x's and the y's. So can anyone remember then our distance formula? So it's distance equals, or sorry, speed formula. Speed equals distance over time. Perfect. Okay. So keeping this in mind now, my speed equals distance over time, we're going to do a little speed question with the kids. So this is all in your T&L. Are you following okay? Okay, perfect. So a woman drives along a 40-kilometre straight stretch of motorway in America as part of her journey along Route 66. Okay? She puts on her cruise control to drive this section at a constant speed. It takes the woman 30 minutes to drive to the end of this stretch of motorway. At what speed did she travel along this road? Okay, so let's have a look at this. So using our formula here then, so our speed will be our distance, which is 40 kilometres over our time, which is 30 minutes. Okay, so she is travelling at a speed of 1 1/3 kilometre per minute. Okay, so, or if we like, we could say 40 kilometres in 30 minutes. Yeah, we could say 80 kilometres then in per hour. Perfect. Okay, so what we're going to do though is we're going to try and represent this on a graph. So from here we've got 2 variables. We have distance and time. Okay, from distance and time then, which one depends on which one? Does time depend on distance or does distance depend on time? Yeah, distance depends on time. Perfect. So which variable then is independent? Time. Perfect. So time is independent. And which variable do we traditionally put on the x-axis? Yeah, the independent one, isn't it? Generally, just traditionally, doesn't have to be, but traditionally the independent one goes on the x-axis. So we'll put time here and we'll put distance on my y-axis. And we will graph this, her journey. Okay. So I'm just going to put her journey up here. Now, so it was 40 kilometres and 30 minutes. Now, why is it that we are representing her journey in a straight line? Yes, absolutely, because she travelled at a constant speed. Perfect. Now, what we're going to try to do is, her distance or her speed then was, speed equals distance over time, and her speed was 1 1/3. Isn't that right? I'm keeping it to kilometres and minutes. Okay. Now what we're going to try to do is, can we relate this formula, speed equals distance over time, can we relate it to the slope formula? y2 minus y1 over x2 minus x1. So you would take 2 points on the
X. Go up 2 points on the X and go across.
Okay, so this point here then would be, this point here would be 30, 40. We probably just take the 0, 0, would we? As the easiest 2 ones there. Perfect. So our m equals y2 minus y1 over x2 minus x1 will equal then, my y2 minus y1 will be 40 minus 0 all over x2 minus x1 will be 30 minus 0, which gives me exactly my 1 1/3. Okay, so what is that saying to me? 1 1/3 is a slope. That's a slope. And this guy is my speed. They're the same. So slope and speed must be the same. So speed is a rate of change. So speed is a rate of change. Another nice way of looking at it is, well, some of the kids might look at it from the point of view of rise over run either. Same difference. So we have my run is 30 and my rise is 40. Perfect. So just depending on what way they look at it. Rise over run. Same difference. Now, so if my speed is a rate of change, what is changing as what changes?
Distance changes with time.
Distance changes as time changes. Perfect. So speed is a rate of change. Distance changes as time changes. Perfect. So what we're going to do now is we're going to investigate more into this, putting context onto the x's and the y's. So what I'd like you to do now is, can you just have a look at page 45? You should see a student activity there. Okay. So you see what we have here. We've the first two filled in for them because that's what we've talked about so far. Number one, the slope of a line measures the rate at which the y's change as the x's change. And you can see what the kids have to do is they have to talk about it in words. The y's change as the x's change, and they have to nominate what's independent and what's dependent. So my y's depend on my x's. We already talked about it for number two. The speed of a vehicle, so that is distance travelled changes as time changes, and as you said, my distance depends on my time, and they have to nominate their independent and dependent variables. So taking it on from there, number three, we might be interested in the rate at which the height of water in a container H changes as time T changes. Okay, so the height of water changes as time changes. So which one depends on which? Height depends on time. So we've got our height dependent and time independent. What about number four? An engineer might be interested in the rate at which the length of a metal rod L changes as temperature changes. Okay, so they have to write in the exactly, the length is dependent on the change of temperature. Okay, so can you see how we're showing them how to interpret what a rate of change is? This is also very important. Well, it's important if they have to graph for a start, but it's also important because we're working our way up to dy dx, isn't it? So that they would look at this question and they would know dld or. Do you understand? They understand what's changing is what's changing. So there's more there for them to have a wee look at. Now what we're going to look at now is, see the next page, you have another activity. And this is really pulling in the prior knowledge again from Junior Cert. Because at Junior Cert, there's a lot of vocabulary around rates of change. And we want to try and remind them of all the vocabulary they have to talk about a rate of change. So we did this back, golly, this is workshop 4 now that we did this. We have a lady here and she is taking a bath. Okay, and this graph represents the time she was in the bath. So I have on my y-axis depth of water and on my x-axis time. So this graph is graphing a rate of change again, isn't it? What's the rate of change?
The depth of water.
The depth of the water is changing as against time as time changes. Okay, perfect. So this rate of change, what I would like you to do now, just on your whiteboards together there for a couple of minutes, will you put a word bank together of all the words you would use to describe the rate of change over the course of this graph? Okay, so this whole graph is describing rate of change. If you were to describe this graph to somebody else, what words would you use? So what kind of vocabulary did you use then? We started off with the hot and cold taps were turned on. So what was the rate of change like then in the depth of the water?
Increasing.
Increasing.
Quickly.
Perfect. Quickly. Rapidly. Steadily. Yeah, brilliant. Okay, and then they turn off the hot tap. So what happens to the rate of change then? It slows down. Okay, perfect. Slows down. And then after that, the cold tap is turned off. So both taps are off and she gets undressed to get ready for her bath. What's happening then?
No change.
No change. Yeah, absolutely. So there's no change. And that's a hard one for the kids, isn't it? That the time is moving, but the depth isn't. So that's why you get that straight line. So exactly, right? So we've no change. Lovely. And then she gets into the bath. So what happens to the water?
Instantaneous rise. A sudden rise.
A sudden rise. Perfect. Okay, lovely. And then again, after that rise, then she relaxes in the bath, and again we're back to no change. And then when she gets out of the bath, how would you describe the rate of change of the water?
Sudden drop.
A drop. A drop, decreasing. Perfect. Okay. So, and it's sudden, yeah, it's a very fast drop, isn't it? And then finally, she pulls the plug and the water goes out. So how we describe the rate of change there?
Decreases to zero.
It decreases back down to 0. Lovely. Now we've basically all our words there, don't we, around what we would use to discuss any rate of change. Like if you ask them to describe an exponential function, say 2 to the power of x, it's increasing slowly, then it gets really fast. Do you know what I mean? It's all the same words that you use to describe rates of change all of the time. So a word bank is lovely, even to put it up on the wall. What's also interesting is we have slow and fast. You can nearly think of those as ones that describe speed as well, isn't it? So the adjectives for speed we often use as well to describe our rates of change as well. So that's perfect. Right. So here we have 2 cylindrical containers, A and B, and they are filled with water. The volume of water increases at the same rate in both. Okay, so the water's being poured in at the same rate into both containers. And the height of both of these containers, A and B, is 12 centimetres. So what I'd like you to do is to sketch a graph to show the rate at which the height of the water level changes with time. So again, it's water level changing with time. And I'd like you to draw a graph for both containers. Put both containers on the one graph, so you can see you have the one graph for them there. And what you're told is container A is full after 6 seconds and container B is full after 24 seconds. So if you could do that now, that'd be great. Slope isn't going to be as steep, isn't that right? Okay, so we've got our 2 lines here. Now again, why do we represent the rate of change here with a line? It's continuous and it's constant. Now what in the question told you that the depth of the water is changing at a constant rate?
Same rate.
So now you see this. This tells you that the water is being put in at the same rate. So the water that's going into the cylinder is going in at the same rate. Okay? That doesn't necessarily mean that the depth of the water will rise at a constant rate. There's something else in the question that is telling me the depth of the water is going to rise at a constant rate. The reason why it's going to retain the constant increase is because of the shape of the containers. They're uniform shape the whole way up, aren't they? Yeah, because if they weren't, might be a different story. Okay, it's the fact that both of them are of a uniform shape the whole way up that's going to mean that we're going to retain the constant rising. Okay, so that's why we can definitely put them as a line. I know that's kind of tricky, isn't it? It makes more sense when you see one then that's not going to fill at a constant rate. Okay, so let's just have a look then at question 2. Water flows into a vessel in the shape of an inverted cone as shown below. The volume of water increases at the same rate as for the 2 cylinders above. So the tap is pouring in at the same rate, okay? But this vessel has the same height and radius as container B. Okay, so container B, the height was 12, wasn't it? Okay. How long will it take to fill this vessel? 8. Okay, why did you say 8?
Because its volume is a third.
Perfect, because its volume is a third of the volume of the cylinder. Perfect. So the cylinder took 24, so this will take 8. Perfect. Okay, so as water is poured into the vessel, sketch a rough graph to show how the height of the water level changes with time. So have we go with this one. This one's a wee bit trickier, isn't it? So explain to me in words how this one's going to fill as the water goes in.
Initially, the height is going to go up really quickly.
Initially, the height is going to increase really quickly. And then what's going to happen? It'll start leveling off. Exactly. It'll start slowing down as the radius gets bigger. Perfect. So, again, this is only a rough graph you're asked for, okay? What we're looking for is that the graph indicates steep, then getting shallower on the rate of change. Steep, then slowing down. Okay, that's pretty difficult, isn't it? It's pretty difficult. Now, what we're going to do, say you did that in the classroom, okay? This would be like the homework that we would send home with them. Okay, so this is back in your T&L. Well, all of this is in your T&L anyway. I know you've seen that. So look at page 48, 49 and 50. This could be like the homework questions. So looking at the graph of cylinder A being filled, here we have our graph. It was filled after 6 seconds. So using m equals y2 minus y1 over x2 minus x1 or rise over run, find the slope of AB. So the slope between A and B. What is it there? Can you see? 2. Perfect. If you can't see, you'll be able to see on your page. Okay, so the slope is 2. Number 2, find the slope of OB. It's the same. Okay, which is obvious to us, but mightn't just be as obvious to the child. Okay, now, what is the slope of the line at any point on the line segment OB? At 2. So the question is then, what is the slope of the line at the point C? 2. I know it all seems obvious, but you see what we're doing here? We're trying to get the child, or the student, sorry, to come from the slope over an interval to the slope at 1 point. The slope at an instantaneous point, because that's going to be all about the calculus, isn't it? So just trying to reframe their thinking, okay? And they do it again then for part B. They should have no problem with that at home, right? But then when they come to this cone one, okay, this is where things change slightly. So they have to use their slope formula again to get the slope of AB. So can you see we've drawn in the line between A and B for them? Then they have to get the slope of OB. So it's all the exact same questions. Get the slope of OB. Now the question is, can you use the slope of AB or the slope of OB to find the slope of the graph at the point C? No. See, we could in the first two, couldn't we? Well, so here we can't, but we could in the first two. So what's the difference? Yeah, it's not a line, it's not constant. So where you have a line, it's easy to go, what's the slope there? What's the slope there? What's the slope there? With a curve, it is not. What's the slope there? I don't know. What's the slope there? I don't know. So here we have a problem. And this sort of brings us into all the investigations around calculus. Let's just say you have a class and you don't think they're quite ready for the cone, or you know, you're staggering it a little bit more. Here's a simpler question. We have two students stand 100 meters apart and discover that it takes 3 seconds for the front of a train to travel between their two positions. Okay? Draw a graph to represent how the distance changes with time during these 3 seconds. Let the position of the first student be at the origin of the graph and put the independent variable on the horizontal axis. Okay, so they've got their graph now of the train passing them, the speed of the train passing them. Okay, at what speed does the train pass the two students? So they have to work that out. Okay, so it's 120 kilometers per hour. The teacher was standing halfway between the students during the experiment to supervise. At what speed did the train pass the teacher? The same. Okay, so it's bringing them from that interval to a point, but it's just a maybe more gentle example. Okay, so what we're going to do now is we're going to have a wee look at Usain Bolt running a race. So what we have here is, in the 2009 World Championships in Berlin, Usain Bolt set the world record for the men's 100 meter sprint, running it in 9.58 seconds. Below is a table of Usain Bolt's split times every 10 meters during the race. Okay, so there's all your split times. So what I would like you to do is, could you answer the first 3 questions for me there? Number 1 then, how fast do you think Usain Bolt ran during the race? What do you have for that? Yeah, absolutely. So speed equals distance over time. Well, we know he ran 100 meters in 9.58 seconds. Okay, so that's 10.44 meters per second. Okay, brilliant. So that's number 1. Number 2 then, do you think he ran at this speed throughout the whole race, 10.44? And why not? What?
Starts from left.
He starts.
Zero.
Yeah, absolutely. So when he starts, he's not going to be at his optimum speed straight away. So he's going to be slower at the beginning. Anything else then about?
He accelerates to his constant speed.
He accelerates into more of a constant speed then, absolutely. And even the shape of the graph even tells us as well, doesn't it? That he did not run at this rate throughout the whole race. Okay, so if he didn't run at 10.44 through the whole race, well then what does 10.44 actually represent? An average. Not the speed, an average speed. So number 3 actually represents average speed. So actually, you know the way with junior cert we do the formula speed equals distance over time. What's more accurate is actually that we're doing average speed equals distance over time. So this gives us an opportunity to clarify that for the kids. It's average speed equals distance over time. We don't really talk about that with the kids too much at junior cert level. You know, they have their questions. I left Dublin at 12 o'clock and I got to Galway at 3 o'clock, and that's so many miles. What speed did I do? So we don't talk about the fact that I'm stopping and starting the whole way. But at this point now, though, we're going to make it more accurate. It's actually the formula for average speed. All right, so keeping that in mind then, can you go on and do the next questions, please? The next set. So you have questions 4 and 5. First of all, you had to then, using a ruler, you had to join 0, 0 to 9.58, 100. So you had to join the two ends of the graph. Then number 2, you had to find the slope of that line. So what is the slope of that line? 10.44. Perfect. Now, number 3. That line that you're after putting in has a special name. So this line is called the secant line. So this is your secant. Okay? And what did you notice about the slope of the secant? Yeah, it was the same as your average speed, wasn't it? So isn't that lovely the way the slope of that line represents the average speed? Isn't that really clear? Okay? So that represents our average speed. So keeping that in mind, okay, how do you think we could calculate Usain's speed at precisely 1 second into the race? Yes, so let's put, so 1 second into the race is right here, isn't it? Okay. Now, do you think his speed is less than or greater than? It's less than this average speed, okay. So do you think 10.44 is a good estimate of how he was running at the very beginning of the race? It's probably not, okay, considering he's probably quite slow. So any ideas on how we could get a better estimate?
Join that to the origin and then recalculate.
Okay, so join 1 back to 0. Join 1 back to 0. And recalculate. So this here is the secant between 0 and 1. So if I looked at this then, using, say, rise over run. Okay, so my run is just between 0 and 1. My rise, let's look at the real map. It looks like it's about 4, we'll say. Okay, so it looks like it's about 4. So 4 meters per second. Now what does that represent?
Instantaneous.
Does it though? See, we came from 0, 0 to 1, 1. So what does 4 represent? The average, yeah, absolutely. So that's his average speed between 0 and 1. It's not his speed at 1, but is it a better average than 10.44? Yeah, it's way better, way closer average. Okay. Could I get an even better average? How?
Put a tangent
Go closer to 1.
No, just put a tangent up.
Well, you see, we're pretending the kids don't know that at the minute. Do you know what I mean? You're trying to think of what the kids would know?
Smaller interval.
Yeah, a smaller interval, absolutely, half step in. So if we went in a half step more, we would get an even better average. Absolutely. So a half step in, we'd get an even better average for that 1 at 1, for the slope at 1. Okay. So we leave it there. Okay. Again, you mightn't get any chats out of the kids at that point, because that's really hard stuff, isn't it? That's just why that question's there, is to give the student the opportunity for the couple of ones that are like, no, don't tell me, I want to figure this out myself. Okay. But we're going to take it a little slower into that idea of better estimates with another activity, okay? So keeping with the athletic theme, then we have a student activity here on Victoria Pendleton. Okay. So have you found it in your workbook? It's just the next page. Perfect. So here we have a distance time graph of the first 10 minutes of a warm-up cycle by Olympic gold medalist Victoria Pendleton. Okay, so here's her warm-up cycle. Over these 10 minutes, what is Victoria Pendleton's average speed in kilometers per minute? Okay, so she is going a distance of 5 kilometers over the space of 10 minutes. Okay, so you're going to have to get her speed there. Okay, and then after that, once you do that, the coach wants to know what her speed is at exactly 3 minutes during this warm-up. So the same as at exactly 1 second for Usain's race, exactly after 3 minutes during her warm-up. To help answer this question, this is what we want the kids to do. Use your ruler and draw in the secants AB, AC, AD and AE. Do you see where we're going with this? Okay, they have to draw in their secants, and you see what they have to do for each secant. They have to get the slope of the secant, okay, and then they have to fill in what is the average speed. So the secant, slope of the secant AB, what is the average speed between A and B? And these two answers should be the same, aren't they? That's what we found out, that the slope of the secant is the same as the average speed. And as they do these, what are we going to figure out? Is that the average, just like we saw here, the average speed, the closer we get to A, is going to be a better estimate of the speed at A. Does that make sense? Okay, so it's a lovely activity because the kids have to get in and draw those secants and draw them getting closer and closer and closer. Okay, and in their head, better estimate, better estimate, better estimate. Because this is really going to help them understand calculus, isn't it? So they get this then. So here we have the slope of the secant starts off at 0.6. So 0.6 kilometers per minute. Okay, and then as we're getting closer to A, we get a better estimate, which is 0.4 kilometers per minute. Okay, so the last one is when they draw in the secant between A and E. Okay, and that's our best estimate for the speed at 3 minutes. How could we get a better estimate? Go closer. And can you see the way we did that on purpose in this activity? See the way we left a good bit of space between A and E? Because what can they offer then? Let's put in? Yeah, let's put in an F. Won't that get me a better one, miss, if we put in an F? So we put in a G. Won't that be even better? We try and get it as close. See, you're trying to pull this out of them, that let's go closer, let's get better estimates. Okay, so what we're going to do is, that's sort of like all the preliminary work done now, isn't it? Now we can go right into what calculus is all about. So what we're going to do is we're going to have a wee coffee so that we're ready for the big stuff now. And what we're going to do is we're going to use this Geogebra file on Angry Birds. Here we have a Geogebra file that just shows the flight path of the Angry Bird. Okay? So what we can do here is we can click on flight path to actually show the flight path of the Angry Bird. Okay, now you can tell the kids that, what type of function is that? A quadratic. But they mightn't just believe you, okay, because they'll be like, well, no, that's a cool game and there's not maths on that game. So what we can do then is, if we take off the background, starts to look a little more mathsy now, and what we can do is show the full quadratic function. And now it looks a lot more like something that they did for their junior cert. Okay, now what we saw earlier today was that if I want to get a slope at an instant point. That it's easy on a line, but it's very difficult on a curve. So what we're going to do is we're going to have a wee look at trying to get the rate of change at that point. Okay? So that is our goal. What is the rate of change at that point? So as we saw today, first of all, for rate of change, we absolutely need a second point, don't we? Because we're going to use the slope formula. So we need a second point. And then as we saw earlier, if I connect those 2 points together, that is a secant. Okay? And it is the slope of that secant that represents the average rate of change between those 2 points. Isn't that it? Okay, so that's the average rate of change. And what we saw is if we're really keen on knowing what the rate of change is at this point here, at 1, 4, the best thing to do is to get better averages, isn't it? So if I pull my secant closer, I will get a better average speed, or a better average rate of change. And the closer I get, the better. Isn't that it? The closer I get, the better. All right, so that's what we were talking about earlier. Now, it's all down to rate of change though, isn't it? It's not about the secant, it's about the slope of the secant. Okay, so we definitely need to do to use slope here. So put on our slope. Put on our slope notation. So what we need here is we need to this point here, the point 1, 4, we call that x1, y1, and the second point we call x2, y2. So my run, as it were, is x2 minus x1, and my rise is y2 minus y1. Okay. Now, here's the story though. And in its present form, we're not using the function in any type of way. Okay? And we really want to be using the function. So you see this quadratic, let's call it f of x. We'd really like to use that function f of x in some way. All right? Also, what we've got going on here is x1, y1, x2, y2. That's a lot of variables. Okay, so we want to simplify down the variables and we want to use the function in some way. So what we're going to do is we're going to change the notation. So we're going to let this x value, this x1, we're going to let it be a. Is everybody okay with that? And instead of calling the corresponding y, y1, we're going to say, well, to get y, you just evaluate a in the function f of x. Isn't that right? So your y value is really f of a. Are you happy with that? Okay. So this is lovely now. We've related the whole point back to 1a and to the function. Now we want to do the same for the second point, x2, y2. So instead of introducing a second x, x2, what we're going to do is write the x2 in terms of the first x. So if the first x is a, my second x, you see the second x is a 6 here, oh no, a 5. Can you see that? Instead of calling this x2, we're going to say it's the same as 1 plus the run. Can you see that? If I go 1 plus the run of 4, I get to 5. And instead of calling the run x2 minus x1, we're going to call the run h. Yep.
At what stage would they have ever come across that at junior cert level where you're talking about a function instead of x's and y's as x's and f of x's? Is this the first time you did?
No. No, y equals f of x will be done all during junior cert. Yeah, absolutely. Oh, absolutely. They should be familiar with this. Where it's difficult is because it's abstract. It's a and f of a. So what you might want to write down for the kids is here's 1, and then f of 1 equals 4. You know, bring it from the numerical to the abstract. So for our second point over here, we're going to say it's this point a plus h. So now my second x is a plus h. Are you okay with that? So that's my second x, and what we're doing to get our y, we are just putting it into the function. So we will put a plus h into the function to get y2, so it'll be f of a plus h. Okay? Now, I know that's kind of abstract, and you might need to let them run some numbers in it to feel comfortable with the abstract version. But what we come to now is that we have lovely notation related to the function and just one point, a. All right. Now, what we're really doing here is, as I said, it's all about the slope of the secant, isn't that right? So the slope of this secant, using my slope formula, y2 minus y1 over x2 minus x1, that's what we did earlier. That's how I get the slope of my secant. Now we're just going to change it by just changing the notation. So y2 is now f of a plus h, y1 is now f of a, and then my x2 minus x1, we've decided to call the run h. So it's divided by h. But it gets you the exact same answer. So there's no difference, only the notation. It's just a fancy slope formula. Okay. So what we're going to do now is we take this, and as we saw, we get our best estimate by bringing it closer. Isn't that it? Okay. Now, can you see what actually is getting smaller? The whole time, what I want you to focus on is the h, the run. Can you see as I get closer that the run gets smaller? Can you see that? So the run keeps getting smaller and smaller and smaller and smaller and smaller. And didn't we say our best estimate really is going to be using the point that's as close as possible to the original point, this one A. So we want to go as close as we can to A. Now, we just have one little problem, because the kids might think, sure, why don't I just go right up on top of A? Can you see what happens there? I'm now undefined. Now, the reason is, if I go right up on top of the point, do I have 2 points anymore?
No.
No, I've only one. And I need 2 points for my slope formula. So that's it, you need 2 points. But what we really want is the second point to be wedged up against the other point, really close, but to not become the same point. And this brings us back then to what we did earlier, doesn't it? This brings us back to how we instruct a function to do something like that, is through using a limit. So we'll use a limit to tell h to get really, really small. Okay, and that way the second point will come up really, really close. So doing that then, we will ask this expression, the slope, we'll ask the slope, will you take the h and will you let it tend to 0? Which means it's going to become really, really small, but will it ever become 0? No. That's the magic of the limit. It's the power of going right up to 0 without becoming 0. Okay? So this expression here is going to give us our absolute best estimate for the slope at that point, or the rate of change at that point. Okay, now just from a sort of diagram point of view, let's just take off these. Okay, from a diagram point of view, we're working with a secant. Okay, it's going all the way up to, right up to this point. Now, it stops looking like a secant when it gets really close. And what does it start to look like? It starts to look like a tangent. Okay? And that's because when you wedge the secant right up against the next point, for all practical purposes, it is the tangent. Now we know technically it's not the tangent because it's touching at how many points? 2. But they're so close together that technically or practically you can say it's the tangent. Okay? So really, if I wanted, I'll just take off the secant there. So if I wanted the slope, if I wanted the rate of change at that point, really all I have to do is get the tangent and find what is the slope of that tangent. Because that's the same as the slope of my best estimate, secant. Okay? So isn't that really cool? Like that is taking it from so hard to so easy. To get the rate of change at that point, all I need is a tangent and get the slope of it using rise over run, x2 minus x1. Okay?